Okay, let me open. Let's review the topic that we covered last time a little bit. We talked about metadata. Okay, for metadata, recall that it's something that is not part of the file itself. So for example, file name is a metadata, right? Or size of the file is metadata. Uh, Timestamps is metadata and so on, right? But recall that file names are not part of the inode. File names are not part of the inode. And the reason for that, first reason is that we need to locate this file somehow. And that means we have to go through all these directories, subdirectories, and so on. And we need a file name, right? So to find that file in a directory. So definitely it makes sense to keep it inside the directory entry and not inside the inode. That's one reason. And the other reason is because we can have so-called hard links, and it doesn't make sense to keep file names inside the inode because multiple places can refer to the same file. So by the way, whatever material we cover today, that can still be in the exam, right? And in fact, it will be in the exam, right? And journal and file systems also from last lecture, that will be in the exam. Please review that. So yeah, so file permissions, so this is also something that we can keep an inode. Recall that we have 1 bit for each permission read, write, and executable. So okay, so then recall that in inode we also keep mappings, right? So we have direct blocks, indirect blocks, double indirect blocks, triple indirect blocks. So that's similar to page table, but the exception is that we kind of variable size page table. So I should say, right? So we start with a really 0 level, right? Then we go to 1 level page table, effective 2 level, 3 level, right? So we first keep it directly in inode, then we have indirect block dedicated to this translations if we need extra space. So as we need more and more space in the file, as it expands more and more, we go to double and triple indirect. Of course, when we have double indirect, we still have indirect blocks. We still have direct blocks, but we kind of expand it more and more. So all these data blocks will be present. So yeah, so sometimes there is a better approaches like extend trees. Well, I wouldn't say there are better approaches, but they have some other advantages. Maybe sometimes you want to have some holes inside the file, like some gaps. And this is where using a real tree can actually help. So also we talked about free list, like how we can, I think we started to talk, right? How we can track and allocate free blocks. So the first thing that we can do, let me remind you, is to use a free list. So did we talk about free list? Yeah, okay, yeah, I think we did talk, yeah. So there is a free list. So that means we keep blocks, one block pointing to another block, then to another block, and to another block. So similar like what we did in memory allocator. So the problem is if I have to allocate 1000 blocks, I have to iterate through 1000 blocks, right? So that I can, because each time I need to retrieve what is the next free block, what is the next free block, what is the next free block. So at each point I have to read it. Yeah, so that is not good. So what can I do? I can use a bitmap. So instead of iterating through different blocks, I will just use a bitmap. So instead of iterating from this to this, like where I have like maybe 8 byte and this is like kind of unused, right? So I will have that's a pre-block list. I'm gonna keep a bitmap. So one bitmap block contains let's say one bitmap block is about 4 kilobyte and each byte is 8 bits. So I can keep 32,768 bits, right? And each bit will represent if the corresponding block is allocated or free. So that means this one will tell whether this guy is allocated or not, right? This will tell if this guy is allocated or not, and so on, right? So I can, by reading one block, I can allocate up to 32,768 blocks. I can already scan that bitmap and see what is already allocated, what is still free. So I don't need to read the entire thing. So that has that advantage. And more complex, like I may sometimes keep trees, can keep ranges of blocks which are available. So that is also sometimes preferable. And for log structured file systems, that's different. That's kind of like a different way to organize it. And yeah, so that one will be kind of converted to sequential writes. I think there's some symbols garbled here, but that's basically means that random writes convert to sequential writes. Yeah, so we looked at the I think we directory names and file names. So let's take a look at this, right? So yeah, so remember that we can mount one directory or one file system to another file system. So we have a root file system as being user, etc, users, and in users we have, admin, right? Right, so in admin directory, we can mount another file system. So by the way, whatever we had previously in admin will disappear, right? So we'll kind of not be able, but typically we want to create an empty directory. But if for some reason you forgot to create an empty directory, the directory contains something else, you won't be able to reach that something else, and instead you will now reach that different file system when you mount. So you'll have A, B, and C. You mount one file system to another file system. So that's how things are organized in your Linux system. You have root file system, like the one that you, the main file system that you use in Linux, and then you mount other things like you connect flash drive or whatever you connect. That appears as a something that is mounted in some directory in the root file system. So yeah, so recall that the file inode doesn't contain file name, right? So we already discussed. So let's take a look at the example disk layout. So what we have is, and by disk layout, I mean a partition. So that means you create a partition, that means placing your disk, and where you initialize it to a file system, right? So the first thing that you keep is a super block. So that's the first thing, super block. Super block contains some important file system related information. So then we have to have inodes. So remember that inodes, I mean, some file system can occupy the entire block, but typically in ext4 or ext3 they will split one block to keep multiple inodes. So that means an inode can be like 256 bytes or 512 bytes, but perhaps your block is 4 kilobytes. So you can fit multiple inodes in the same block. Yeah, so you'll have a bitmap of inodes. So you have a super block, then you have, let's say, inode bitmaps, and that will say this inode is free, this inode is allocated, this inode is again free, and so on. Of course, then after inodes, you're gonna have the data region. So this is when you're gonna keep your data, and also I shouldn't say just data region. For example, if your directory contains some tree structure, right, on some file systems, that's technically metadata. But you allocate blocks from that region, right? So from this data region. yeah, so that's just, you know, just to clarify that. So after inodes, you have normal disk blocks. So and for disk blocks, you have you know, data bitmap, D bitmap. So that will say this block is available free, right? At least on this ext4 file system. Yeah, so but in general, you know, doesn't have to be like this. It can be a different way to implement it. So it can be tree, as I said, maybe it can be just a list of free blocks depending on the file system. So now let's say we have some inode, inode 5. Right? So inode 5 is allocated. So if we kind of look at this inode, like what's inside, we have, okay, there is you know, we have the size, right? So we have timestamps, owners, so on, right? Then we have direct blocks, indirect blocks, double indirect, triple indirect blocks. Okay, so let's see what happens here. Direct blocks will already point to the region of blocks. So that's going to be block 36, I guess, in this picture, then 37, and so on, right? So then let's say the third block will point to 32. So again, the region that it points to doesn't have to be contiguous, just like in a page table. You can have a contiguous range of file offsets, right? Which map to non-contiguous disk blocks. So it can be any order, anything, just like pages. So basically, yeah, so basically you have some blocks here, mapping for direct blocks. And let's say, and at some point, let's say in this block, maybe it was a directory, maybe the inode was for a directory. And that directory contained information about some other files. So remember, directory is a special file which contains information about other files. So that will be a file.txt name and corresponding inode 34. Or subdirectory and corresponding inode number 7. Okay, so 34 is also allocated, right? So that will point to the inode table. So 7 is also allocated, also an inode table. So let's see what will, and again, this information is kept somewhere in directory data, right? Which is part of the direct blocks or whatever it is, right? Maybe it's already indirect or double indirect, depending on the size of the directory. So the directory can also be very huge, right? So now let's say we want to open or read a file. So what we will do? So we open home Ruslan file.txt and retrieve the file descriptor for that, right? So let's see, that's the interface. So let's see what will actually happen. So, and then we, of course, we're going to read from that file. Maybe we're going to read 1 kilobyte. So let's see what will happen with the open operation. So we read inode 2. Let's assume that the root directory is kept in inode 2. And again, that information can come from the superblock. So the superblock can say the root directory of this file system at this inode number. So this is where you start, right? So you start searching that file. Okay, you read inode 2, that corresponds to the root directory. So again, that's, if you look in detail, we can see that what inode contains. Just give me a second. Yeah, so that will contain mode owners, right? So file mode owners, timestamps, you know, so on, right? And then direct blocks, indirect blocks, so on. So we read these blocks so that we want to retrieve the contents of this directory, right? Okay, we find inode number for home. So because now we want to go to the next inode, which is home. So we find a home entry in the corresponding inode. Okay, we read inode for home. So previously we read root inode. Now we read home inode. So we again read the contents of that block. Find inode for Ruslan, right? That's another entry. Okay, read inode. Again, now we're in that directory. We're gonna find file text, right? Find inode number for file text. Again, we read inode for file text. Finally, we check if we are about to open that file, right? We're about to complete this open operation. But before we complete, you need to check whether you have permissions to access this file, especially for the specified, you are specified to open for reading and writing. Okay, then you have to check the permissions of the file. First of all, you want to check if you are the owner of this file. Okay, if you are not the owner, are you at least in this group? No, you're not in the group. Okay, then you belong to everyone else, right? Then you look at the corresponding bits. Okay, so and then you'll see whether you have that permissions, like reading permissions or writing permissions to access that file. If you don't have that permissions, it'll say, okay, permission denied, right? So you cannot open that file. So that will return an error. Otherwise, it will succeed. And then, you know, if it succeeds, we will allocate a file descriptor slots in a file descriptor table. So remember, there is a file descriptor table which is in each process, and whenever I have a file descriptor, I can basically the number of file descriptors is limited, right, from 0 to let's say 1023, right? And I can also keep some bitmap in memory to manage that file descriptors, which one of them, like to detect which one of them is well, which one is already allocated. So that's the way that typically implemented. And then you have basically an array which translates a file descriptor to a file description. And that file description inside the kernel is basically a pointer to an inode, right? So now you have this inode address. So you know what inode you need to open. And inode typically is also going to be cached in memory. I mean, especially if you just open that file and we're about to read it later, right? So we allocate a file descriptor, just find any available file descriptor that is not used yet and establish the connection between that file descriptor and file description and the inode, right? So now the user gets the result, file descriptor. So then the next operation is read operation. So in the read operation, you specify this file descriptor. So we have to, now we have the file descriptor, we can get the file description inside the kernel, right? Which is just a pointer from the table. And then from that, we can get an inode number. So getting the inode number from that allows us to basically do operations on this file. So we now can read the corresponding inode. We can read the corresponding data. So we're gonna get the first direct block, and get the second direct block number and read the corresponding second second block, right? So maybe you have 512 bytes blocks on the file system and you read 1 kilobyte. So you will read a couple of blocks and you are done, right? I mean, or maybe if you have larger blocks, 4 kilobyte, perhaps you don't need to even read the entire block. You need just to read partially this first 1 kilobyte. Or maybe you have megabytes then, or gigabytes, then you potentially need to go to indirect, double indirect blocks and so on. Does it make sense? Okay, so some of these things may also appear again in the final exam, as I said. So like, because whatever we cover today still can appear in the final exam. So what about partitions? So partitions is probably the term that you have heard in the past, right? And you probably use that. You will create multiple partitions on your computer, maybe, right? So I don't know, right? So that's basically the idea is to split storage into a range of blocks. So we have a logical block number. We create a partition 1. You decided, okay, on block 0 and block 1 are going to belong to partition 1. 2 to 5 are going to belong to partition 5. 2 to 5 are going to belong to partition 2. Of course, probably your partitions are going to be much larger than a couple of blocks, but still, right? So that's just an example. Yeah. So it should be a contiguous range of blocks. Contiguous regions. One thing to keep in mind it's a fixed size. So it's difficult to resize. So once I created this partition, once I created a file system inside that partition, how do I deal with this, right? So if I need to increase it, well, maybe there is another file system in the second partition. I need to shrink it, and to shrink it, I have to move inodes. I have to move all this metadata and data that I have allocated, and that is not easy. And not to mention, even if I wanna, increasing the size of partition is probably not that hard. If you have some extra space, but shrinking is hard, right? Because I can already allocate something in that region. But even increasing size sometimes can be challenging because maybe you didn't have any bitmap data blocks for that in the past, right? So now you have to keep this bitmap. Certainly you want to use some special tools for that. And those tools are, I wouldn't run them unless I have a backup copy, right? Because what if they fail and I lose all data on my partition? Okay, so how do we store partitions? So we store partitions in a partition table. So if you used some legacy systems such as BIOS, right? So I guess until recently, there was still quite a few computers with BIOS, and we would have master boot record. So that's the very first disk block you have, and that specifies 4 partitions. So if you need more partitions, you typically create an extended partition, and that extended partition has another block which defines for more partitions and so on. And that potential can create as many partitions as you want. In modern systems, like you have UEFI instead, and that is replaced with the GUID partition table, GPT. So don't confuse it with Chat GPT, right? So that's GPT. So that allows you to keep like maybe 128 partitions, if I remember correctly. So that doesn't have the same restrictions as MBR. But the idea is pretty much the same. You just keep the starting address and how many blocks you need. So also let's talk about hard links. And again, this material that can appear in the final exam, right? So hard links versus soft links. So hard links, we already briefly mentioned what a hard link is. So it's basically an alternative name to a file. But a hard link, how do you create a hard link? So you create it using the len command. So let's say you have a file name and inode number in one directory. And in some other directory, you have other file name, maybe completely different file name, but with the same inode number. And that points to exactly the same file. So effectively, your file system is not a tree, actually. It's more like a graph, right? So that's where multiple directories have different file names, and they are pointing effectively to the same file. So that's no longer a tree, right? Of course, I guess it's not a common case, but still you can see that. So for example, I have home Ruslan 1.txt and home Alice 2.txt, and they are pointing to the same file. So when I change 1.txt in one directory, like maybe changing permissions right into that file, 2.txt is also automatically changed. So this basically two files are the same, right? So they're basically just an alternative name to the same file. So this is also the reason why we don't want to keep file name in inode, because the moment we keep file name in inode, then we are kind of restricted to this name. But we really have two different names. So now one thing that you may wonder, how do we remove that file? How do we know at which point we remove that file? So let's say we remove other file name, right? So we remove home ls2.txt. So what happens with that file? well, we still cannot remove it because there is another file name that leads to the same inode. So it's just dereferences that. So we effectively gonna have a reference counter. So inside the inode, we're going to keep how many references are leading to this inode. So currently there are 2 references. So the reference counter is going to be 2. So when we remove it, we're going to decrement that reference count. So it's now going to be just 1. But it's still 1, it's not 0. So therefore the file will still exist. So and when finally we remove the second reference, then the reference counter will reach 0, and at that point, this inode can be fully removed. So this is how you will support removal. Again, this is not doesn't require anything crazy, just the reference counter. So and the reference counter is just an integer number, like just 4 bytes or 8 bytes, whatever we keep inside the inode. Okay. So soft link or symbolic link is a different one. So this one is created as ln-s, and I guess this one is more common nowadays. So that is different. That is actually a different file and a different inode. So you have a special file which has a path to another file. Effectively, right? So it's just a special type of file, just like a directory is a special file which contains information about other files. So a symbolic link is a special file which has a path to another file. So basically, its entire content is just a path. So we have other file name, right? So our inode number points to this special inode, right? So the special, I mean, it's not special, just a regular inode, but a special file. So that contains a path to the file, and that will lead us to the file name. So let's say home ls dot text is a symbolic link, so it will contain a path to home Ruslan1.txt. And that will open another file, right? So that is now we have another file name which corresponds to another inode number. So whenever we open home ls1.2.txt, that will redirect me to the original file that it points to. So by default, it will open that file like from home Ruslan1.txt, right? So that will go to that file. There is a way, of course, in open to specify that you don't want to follow the symbolic link. I think it's called on follow or something like this option. But by default, it will go and follow that link. And, what will happen is that, maybe you're going to follow that directory, but then turns out that home Ruslan is also a symbolic link. Maybe the entire directory is symbolic link. Not to mention that one text can also be a symbolic link. So there might be multiple like iterations before I actually reach the final file. So at every point, I can have another symbolic link, and that can point to another symbolic link. I mean, of course, the file systems at some point will limit the number of symbolic. I mean, typically 8 or 16. After they say, okay, there is just too many recursions, and at this point, I don't want to iterate anymore, right? Because otherwise it will go to an infinite loop. So there is some, of course, reasonable limit to that, but you can have as many symbolic links as you want. And symbolic link, of course, can point to hard link, because the hard link is effectively just an alternative file name, right? So anything can happen, right? So all combinations are possible. So the difference is the hard link is still the same inode number, just an alternative name. Symbolic link is a special file which is kept in a separate inode, which contains a path to another file. Okay.
Why do we want to be able to do both? Why don't we just have like a hard link soft?
Well, there is some problems with both, right? So it's a good question. So with hard links, what is the problem? With hard link, it's not easy to, let's say if a home Ruslan limited to 1 gigabyte, Alice may take a free ride, and just this quarter will basically going to be accounted to me, not to Alice, right? So maybe Alice has a 1 extra gigabyte, which would otherwise she wouldn't have, right? So then that's one problem. So these quarters can be an issue. So there's how you manage this. And also it's hard to determine what was the original file at that point. It's not clear who is the original owner of that file and so on, because it's just an alternative name. So symbolic link, however, will have other issues. Sometimes you can have a broken symbolic link. It points to a file which no longer exists. So unlike hard link, which is impossible, right? So the file will always exist. So soft link or symbolic link can be broken. So maybe I have, home user local whatever, right? Pointing to I don't know, home user local GCC points to sorry, user local bin GCC points to user bin GCC, but user bin GCC doesn't no longer exists. So when I execute user local bin GCC, it fails. Does make sense? Yeah, so there is different pros and cons. But I guess overall, I guess people would probably prefer to use symbolic links because at least it's kind of has less issues and it's more kind of transparent that it's actually a link, right? Not some alternative name. So in that sense, yeah, I guess they're more common nowadays. But hard links are still there. You can still create a hard link. You can try it on your computer and can create a hard link. So also keep in mind that permissions, symbolic links may have their own permissions, right? So, I mean, of course, they have to satisfy the permissions of the original file. You still have to be able to access the original file, but symbolic link itself can have some different permissions. Like whereas hard link, both file names will share the same permissions. So the moment I change one file, the other was also going to be affected. I mean, I guess it also happens the same soft links because you only have eventually one file, but the link itself, you can also put additional restrictions. Okay, so symbolic link is just a shortcut to another file. So just be mindful how many inodes you have to traverse in each case, right? So as an example, right? So how many inodes you traverse in symbolic links and hard links. So in terms of consistency, so what happens if power fails or system crashes? So, we talked about journaling already, right? So, but if you don't use journaling, the classical solution was to run a file system checker, just like malloc heap checker, except that it tries to fix problems, right? In malloc heap checker, you would check and say, okay, your heap is corrupted, but you won't do anything about it. So now your file system is corrupted, but you will try to fix it. Of course, that's like you can try to fix bitmap. You can say, okay, there is some referenced inodes, and you didn't mark it in bitmap or whatever, right? Unreferenced inode, maybe some orphan files, you put them in lost and found, right? So there is different kind of possibilities, right? So so maybe you lost some direct, you don't know where it is, right? So now it has to be placed there. Yeah, so basically, it's best effort guess using corrupted data. Of course, it's not 100%. Of course, in some cases you will fail, and so it's not fully kind of failure proof, right? And it's inaccurate and really slow. It could take hours before you complete the operation. So, and as I said, by the way, it's also file system specific, right? So it's a complex code for each file system, because for each file system, you need to know its structure to write this file system checker. So the second solution we have discussed was journaling, right? So I guess the third one is log structured file system, but we won't talk too much about this in this course. So journaling, please review journaling because that again may appear in the final exam. So anything that we cover can appear, right? Okay, give me 1 second. So I'll switch to the last topic that we will cover in this course. Okay, so the last topic that we will cover, and again, it's something that can appear and will probably appear in the final exam, in some way, right? So I'm not saying that we will have too much of that information, but something that you can still expect about this topic. You know, so that's called RAID, right? So RAID is a redundant array of inexpensive disks. So what is the problem of RAID? Well, sorry, not RAID, not the problem of RAID, right? So what is the problem with regular disks? The problem is with regular disk is that storage is slow, right? So especially, I mean, with SSDs, it's of course not that bad, but with hard disks, it's a really big problem, right? So, but even with SSDs, it's not ideal. Sometimes you want to be faster, but with hard disks, they're still in use. You know, especially we need to keep a lot of data, and you don't care about speed and so on, right? So you wanna care a large amount of data, right? So at that point, maybe you want to have cheap storage. Also, you want to use hard disks, but the problem is that they're slow, right? They're really slow. So what is the solution? To use more of them, right? So just basically use more hard disks and make them faster. Or maybe also another problem with hard disks, they are not reliable, right? So maybe they fail a lot, right? So maybe you, again, to improve reliability, we can use more of them. So redundant array of inexpensive disks is RAID, right? So that's the solution for that problem. So let's talk about that. So the first approach is RAID 0 striping, right? So you split your data across multiple disks. So let's say we have a traditional way to store data. I go and write my data 0 block 1, 2, then I continue to the next disk 3, 4, 5, 6, 7, 8, and so on, right? But I can do something smarter. So what I can do, I can just split it across different disks. So block 0 gonna go to the first disk, 1 to the second disk, 2 to the third disk, and so on, right? So why is it useful? Okay, go ahead.
There's usually access data in sequential.
Yes. So, and it's not just even sequential order. So for example, disk block can be 4 kilobyte, but my file system block is 16 kilobyte. So I may as well just request, and I have, let's say, 4 disks. I may simultaneously read 4 blocks for 4 kilobyte blocks, and that's 16 kilobyte block that I have in a file system, right? And not to mention that there is sequential data, right? So then I can read even more data in parallel. Yeah, so that's the advantage. That's for reading as well as for writing. So I can write in parallel, I can read in parallel. So that is definitely better than option 1. Because with option 1, we can only read one disk or write to one disk at a time, typically. Here, all disks will be busy, right? So assuming they are they have the same performance, we should basically triple writing reading time. Okay, but there is a problem, of course, with that. So let's say what is the characteristics that's used for to assess how many kind of how frequently we need to change our stuff, right? What is the how do we can assess these failures, and how can we deal with this? So there is a metric called mean time between failures. And for example, you can see 1.2 million hours. Okay, that's like a lot of time, right? So that's like 137 years. So that's like, it looks like I'm done, right? So I can buy that storage and be okay with this, right? So am I done buying storage for life? No, right? So that's just marketing, right? So that's just, in practice, you probably will have to replace it sooner. Okay, let's look what this mean time between failures is. So the correct interpretation will be failure rate is 1 over mean time between failures. So, but what if you have a large 10,000 disk cluster? So you just create maybe this RAID 0 array of 10,000 disks. So any disk failure can, like any disk failed, you lose your data, right? At least, I mean, it's a reasonable assumption because, you know, a significant portion of the file will be lost. So then the failure rate is going to be 10,000 over mean time between failures, and that's 1 over 5 days. So that's basically a failure every 5 days. So something fails every 5 days. So yeah, so that's much worse, right? So I mean, of course, maybe it's a little bit exaggerated example, but you know, you will be expected to change a hard disk all the time, right? So that's a problem. So what is the other solution that we can use? Yeah, I mean, they definitely need something that is more that allows us to improve reliability, right? So again, mean time between failures is really confusing sometimes, right? So we can use RAID 1 mirroring. So we keep redundant copies of data. So we have 0, 1, 2 on one disk, we have 0, 1, 2 on the second disk, 0, 1, 2 on the third disk. So what is the advantage of that? Well, now we have a redundant copy of exactly the same data. If one disk fails, I still have another disk. And if even that fails, I still have another disk, right? So I improve reliability. So therefore, yeah, so improved reliability, right? So that's the advantage. But of course, there is some negative sides of this, right? So it's going to become expensive. We are wasting a lot of space. You know, so it's even worse than just a regular, right? So like a case when I use one disk, then another disk, and third disk, and so on. So what can we do? Well, first of all, before what we can do, let me ask this question. So in RAID 1, what would be that? Does write speed? What would be the write speed compared to a regular disk? Okay, go ahead.
The exact same.
Yeah, it's pretty much the same, approximately, right? As long as you know all disks are the same, right? So what about reading speed? Why is it slow? No. Yeah, it will be faster, right? Yeah, because assuming it doesn't fail, like the other all disks working correctly, you can simultaneously read 0, 1, and 2, right? From 3 disks. So reading speed can still be faster, but writing speed will not be faster. So that is an advantage of RAID 1, right? So what else can we do? Well, we can combine best of both worlds, right? So we can have RAID 0, 1, RAID 0 plus RAID 1, right? So we can have RAID 0 arrays, and they are combined as RAID 1, right? So we treat a RAID 0, each of them as like one individual disk and combine it as RAID 1. So that's one possibility. Or we can do the opposite. We can have RAID 1 and combine them RAID 0. So that's going to be RAID 1, 0. But the problem is that I mean, the advantage, of course, is going to give you good performance, good reliability. So it's kind of, we'll try to give you both from, like, you know, we'll give you good things from both worlds, but it's still expensive because you are still wasting a lot of disks. So what else can you do? Well, yeah, so we can lower the cost. We can use error correction codes, right? So, and one specific way we can deal with this is to use parity. So the parity will determine the odd or even number of ones. So we have some number, right? So let's say it's 0, 1, 0, right? How many ones we have? Just one, right? And is it odd number? Yes, it's odd number. So therefore, if it's odd number, we'll write 1. If it's even number, then we'll write 0. So like in this table, 0, 0, 0, that's we don't have any ones, right? So that's 0 ones, right? So that means it's an even number and the result is 0. Then we have 0, 0, 1. We have 1, we counted just 1, right? So okay, that's an odd number, 1. 0, 1, 0, the same thing, right? That parity bit is 1. Now 0, 1, 1, we have 2 ones. So that's an even number. So that's going to be the parity bit is going to be 0. And so on. You can just look at this table and check that, right? But how can we calculate this? I mean, aside from just counting this once, we can calculate parity by using the XOR operation. So we can just do X, XOR Y, XOR Z, and so on. So, and you can check that that's going to be the same thing, right? So you can go for this table. When you do XOR, it's going to be the same result, right? But how can we recover from failures? So let's say Y is gone, right? So disk has failed. So what can we do with this? So we can calculate X, XOR Z, XOR P. So we can change those, right? So if you know, like XOR, in XOR you can interchange those. So now we can get Y. Even though it's lost, we can recover it from this parity bit. So the same deal with others, right? So we can recover X, we can recover Z, as long as just one failure. I mean, one disk failed. Yeah, I can recover. More than this, sorry, I cannot recover. Yeah, so that is something to keep in mind. Okay, go ahead.
RAID 0 or RAID 1 or RAID 01?
Well, we'll check what you can use, not RAID 0 or RAID 1, right? So RAID 0 and RAID 1, they're not using it, right? But let's look at some other schemes that are using it. Yeah, so effectively you can always recover. Okay. By using this parity bit. So by the way, you can easily prove that it's going to be the same thing, like let's say y xzp, right? So why is that, right? Recall that p is x, y, and z XOR, so that we can replace p with x, y, and z. So then we have x and XOR x, that cancels out, that's going to be 0. And z and XOR z is also cancels out. So like whenever do XOR with yourself, that's 0. Yeah, so then you get y, right? So that's why it's 1. So you get the result here. So yeah, so as long as, yeah, so XOR allows us to recover. So what you can do, you can have a parity disk. So you're gonna keep a disk of parity rather than replicating all data. So you have disk 0, disk 1, and disk 2, right? So now in the first disk and the second disk, you do XOR 0, XOR 1, that's the parity, right? And so on. So it's good reliability at lower cost, right? But not as good in terms of performance. So why is it not as good in performance? Let's take a look what will happen. Suppose we want, so I'm sorry, there is some garbled symbol, but that's basically, suppose we want to change A to A prime. So what will happen in that case? So the steps that we're going to take, I mean, at least what you would naturally think, right? So, I mean, well, the first thing that comes to your mind, you're going to read B, C, and D, and write A prime. To write A prime, you need to write A prime XOR B, XOR C, XOR D. Is that what we actually need to do? No, right? So that's not right. Yeah, so well, instead, what we can do, we can read A and read the parity, right? So the current parity A, B, C, D. So now because we have A, we can cancel out this A in the parity, right? So we can do a XOR with A and add this XOR A prime, right? So it's going to be A prime XOR A XOR the parity, right? So that way I can get a new parity bit. So I only need to read A to write new A prime. But still, the problem, even though I need to just read A, it still requires to access parity, and that becomes your bottleneck. So that's an issue with rate. So that's with an issue with rate 4, right? So this is rate 4. Yeah. So what is the final thing that we can use? Rate 5, right? So that's stripe parity. So we will spread it across different disks. So now what we can do, we will write 0, 1, and then the parity disk will contain 0 XOR 1. Then we have 2. The parity disk will now be the second disk, not the third disk. And 0 and the third disk will contain data, right? So 0 and 3, right? And then finally, the first disk will contain the parity. So we'll spread this parity across different disks. And by the way, when I say parity, it's because it's not one bit. When I mean like it's a parity block, right? So it's like one block, you XOR with another block, you get the parity block, right? That you keep in a different disk. So now this parity is spread out. Why is it important? Well, because remember that parity was the bottleneck here. Now it's not no longer bottleneck. So now because it's spread out, I can read it simultaneously from multiple disks and update it in multiple disks. And also not to mention that, so that still allows us to have this good reliability, because as long as we have just one failure, we should still be able to recover. So it's low cost and good performance. So in that sense, it kind of tries to combine the best from everything, right? But the problem is still just one failure. So there is one variation, rate 6 will tolerate up to 2 failures by using more advanced error correction codes. So that's just a variation of that. Okay, so I guess we are done with this. So again, rate, I'm not saying that we will have something crazy about rate, but some questions you may still expect about rate, right, in the final exam. And any topics that we covered today or previous lectures, so that you should still be expecting. By the way, any topic that we covered in midterm can again reappear. And more specifically, I would recommend you to review the midterm sample exam, to review that material, review the midterm itself, right? So, I mean, aside from just reviewing topics, right? Just review that material. And in addition, I will publish additional sample questions, but of course they will not contain the material before the midterm. So you have to still review both. And I will also publish answers maybe in, a couple of days or so. I want to give you some time to explore question and then compare your answer to the correct answer. So that way it's better, because because sometimes the more important thing is to not answer the question, because you want to have you will not have exactly the same question on the final exam, right? But more important to understand the topic. So kind of to guide you to prepare for the final exam. So final thing before before you go, right? I want to remind that the final exam. Let me open that and Canvas. Give me 1 second. So the final exam, go to syllabus, right? So the final exam will be held in one location. So that's going to be forum building. So that's going to be the same place, I think, where we had the midterm exam, if I remember correctly. So the final exam, let's see, what's going on? Yeah. Oh, okay. Yeah. Okay. Yeah. So final exam from 12:20 to 2:10, right? So on the December 12th, and this is forum building 105. Yeah. So Yeah, so please come to that location. I know that line path mentions 2 locations, I think. But we will have, I think this room is big enough to do it for everyone, and just like we did it for midterm. So let's have it in one location, especially because we have limited number of TAs that can come help me proctor the exam, right? And it's going to be in just one location, and same time for both sections. So again, just come to that forum building, right? It's the same place. So it's going to be longer. So some people ask like how many questions? Well, I would say roughly, right? So I'm not going to say the exact number, roughly like 25 questions, right? So that means you it's going to be longer than the midterm. Again, review all this material, and we may have some Slack discussion. I may be able to kind of answer some questions, but if there's some important preparation question. But otherwise, I wish you good luck and great career and good luck on your final exam. Okay, well,
So at the last, before the midterm, you had a session where you explained these new questions and answers. Will you be having something like that, or?
Well, sample questions, as I said, I will publish that additional, but I will publish additional questions, not the entire thing, right? So because we already had midterm, you can review those questions, and additional review new questions.
So you have that session where you explain the answers, like if you don't understand the answers, will be like a video recording or?
Well, that we explained for the real midterm, not for the not for that's how well, we did it for the actual after exam. Here we won't have it, obviously, right? Because that's the last thing, right? The final exam, right? Okay.
Thank you.
Yeah, just a second.